Simulation, discrete variable. In preparation, please have the spreadsheet open on your computer and follow along. Maximum benefit guaranteed. Learning objectives. Simulate a generic discrete variable given its distribution.
Wow, that is close.
You wanted to know why it all works? I'll explain this by simulating a discrete variable x whose underlying distribution is given by this table.
There's no clear pattern to the numbers.
Yes, Lisa, we deliberately want the general case. Notice we also have the CDF for x in the table.
What does it mean to simulate such a variable?
We must create a set of values between 0 and 5 whose frequencies mimic the probability mass function. We'll begin by generating a set of numbers, let's call it S, which are uniformly distributed between 0 and 1.
Sounds familiar.
And then we'll map each of these numbers to a value of the random variable x based on the CDF of the variable. So what I'll do now is to get to a spreadsheet and generate the 200 random numbers. I'll generate the random numbers now. We are going to use the rand function and propagate this down the column just to make sure we have 200 entries over here. Here's how this works. If our generated number is say 0.1, then it is less than 0.11 and I'm going to map it down to x is equal to 0.
Let me guess. If the number is 0.3, then we'll map it back to x equal to 2.
Absolutely, because it is between 0.29 and 0.52, I'm going to map it back to x is equal to 2. All numbers between 0 and 0.11 get mapped to x is equal to 0. So x will be 0 with a probability of, you guessed it, 11%. And so on. Numbers between 0.11 and 0.29 get mapped to x is equal to 1. The chance of this happening is 0.29 minus 0.11, which is 18%.
I now get why the CDF is key to the simulation.
It's time we put all of this knowledge to test on our spreadsheet. We'll make use of a nested if statement for the lookup. Let's begin with the first mapped value here. It is 0.64. So I will say if this number is less than the very first CDF value, map it to 0. And of course, I'm going to give it a $sign in the appropriate places. Otherwise, if the same number is less than the second CDF value, then map it to the second x value, dollars again. If C5 less than the third value, then it's 2, dollars again. Otherwise, if C5 less than the fourth value, then it is F8 with a $sign. So as you can see, the very first number changed. So I will go ahead and freeze this column so it won't be confusing anymore. Pay special as values. So we can see that the random number of 0.78 has been mapped to 5, and that's right, it's between 0.74 and 1. I'll propagate this down the column. How about 0.42? It's between 0.29 and 0.52, so it gets mapped to 2. What about 0 over here? Yes, 0.05 is less than 0.11 and therefore it is 0. You get the idea. Finally, let's compare the predicted and observed counts once again and then build a clustered column chart. So my predicted count for 200 samples will be 200 times the PMF. I'll propagate this down. What do you think the total is going to be? Sum of this, which should technically give me 200, which it is. The observed count, I will just use a COUNTIF statement. My map values are in column D, and I'd like to compare them to the x values here. I'll propagate this down, and once again my total is 200. With my x values, my predicted counts, and my observed counts, I will create a clustered column chart and remove the x values, of course, and you can see how close they are.
Fantastic match! This stuff is magic.
Of course it does. The logic is quite clear, right? There we have explored a powerful mechanism to simulate discrete variables. For you to really internalize this, we've created some exercises.
I'll go simulate $50,000.
If only life were this simple, Lisa.